This was the dose of coffee I did not have in the morning. Woke me up pretty quickly. Okay. We can start.
I'm just feeling cold, so I just
You want to start? Sorry, let's start back up.
Yeah, maybe we'll start again. Huh?
No, I'm just going to keep a hawk-eyed watch on everybody.
Let me just. Oh, I'll have to get back the.
Okay. Yes.
Yeah.
Yes.
I think I'll start from the beginning.
Yeah, I think so.
Yeah.
That's what Lewis Carroll said. That we should start at the beginning.
Let's start at the very, or in Sound of Music, let's say, let's start at the beginning. So the topic of my talk today is quantum diffusion law. So we all know that Brownian motion is the random motion of particles suspended in a fluid, resulting from their collision with fast-moving molecules in the fluid. At room temperature, the law of diffusion is given by the well-known Einstein's law of diffusion, where the mean square displacement grows linearly with time, with the coefficient of proportionality being given by the diffusion coefficient. Now, the question is, what happens to this law of diffusion as we lower the temperature to close to absolute zero and scale down the size of the Brownian particle? This is our question of interest. Our initial investigation started about 3 decades back, and it's contained in a paper, Brownian Motion at Absolute Zero, which was written by Raphael Sorkin and me, and it's published in Physical Review B in 1992. We have recently revisited the problem, and the motivation was twofold. First, experimental contact, since recent technological advances have made experimental realization possible. And secondly, an improvement in our theory, which I will elaborate on as we go along. This improved theory has been published as a paper, A Quantum Diffusion Law, and was written with Urvashi Sathpathy and Raphael Sorkin, and appeared in JSTAT in 2017. Our analysis is based on the fluctuation dissipation theorem. This theorem is, because of the analysis being based on the fluctuation dissipation theorem, it is independent of the details of the system and therefore widely applicable. This is to be contrasted with earlier attempts by Ambegaonkar, for instance, where they had assumed a model of a harmonic oscillator linearly coupled to a large bath of oscillators. In the quantum domain, we find that the mean square displacement grows logarithmically with time. The fluctuation dissipation theorem connects the linear response of a given system to an external perturbation and the correlation of fluctuations of the system in the absence of the perturbations in thermal equilibrium. The two key ingredients that go into this theorem are causality and linear response. Our analysis is based on the fluctuation dissipation theorem and is therefore general and independent of the details of the system. So just a quick recap of the linear response theory. So consider a system governed by a Hamiltonian H, which is made up of two parts, H0, which is the unperturbed part, and HF of t, which is the perturbation, and which is of the form minus A times f of t. The time evolution of the density matrix of this system is governed by the von Neumann equation, with, and we use appropriate initial conditions. Now, expanding the density matrix and retaining to linear order in the perturbation, we can express the deviation of an operator, say B of t, from its unperturbed value. By using the von Neumann equation, we can express it succinctly as the convolution of the response function with the perturbation force, where the response function is given by the expectation value of the commutator of the operator A, which appears in the perturbation, and B, which is the operator under consideration. Now, because of causality, R of t minus t prime equals 0 for t less than t prime. So taking causality into consideration, we can express the response function R of t in this form. R of t minus t prime is equal to 1 over I h bar times expectation value of the commutator of A and B, and with this theta function, unit step function thrown in to take care of causality. So the fluctuation dissipation theorem is a relation connecting the response function, which is a commutator as we noticed, and the correlation function, which is, because it's a symmetrized correlation function, it is an anti-commutator. It's the expectation value of the anti-commutator of A and B. So
Everything okay?
yeah, this is fine, but I just couldn't see some part. Yeah.
Okay.
Yeah, fine. So the fluctuation dissipation theorem in the Fourier domain can be expressed explicitly in this form. The imaginary part of the Fourier transform of the response function is connected to the Fourier transform of the correlation function via this functional form, tan hyperbolic pi beta h bar nu, where beta is 1 over kBt, T being the temperature. And this is essentially the Fourier domain version of the fluctuation dissipation theorem. And as we saw earlier, R of t and C of t can be expressed as a commutator and an anti-commutator in the time domain. And the quantity of focus for us is, in fact, the correlation function. So from the Fourier domain version of the fluctuation dissipation theorem, after doing a Fourier inverse transform in the time domain, we can express the correlation function in this integral form, where R of t appearing here is the response function, and it's multiplied by a combination of cot hyperbolics. Notice the appearance of crucial time here, T thermal, which is given by beta h bar over pi, is the thermal time. Now, because we are interested in diffusion, the quantity of central interest is the mean square displacement, delta x squared average, which is given by 2 times the difference between the correlation function at time t equal to 0 and the correlation function at time t equal to t. And more explicitly, we find that the mean square displacement is given by in this integral form, where R of t, the response function, appears, and this combination of cot hyperbolics. Now, there are 2 crucial positivity conditions which come into play. So the 2 key physical requirements are Whiteman positivity for the position correlation function and passivity, which is essentially the second law of thermodynamics. It's a statement of the second law of thermodynamics. Now it turns out that the choice of the response function is crucially guided by these two positivity conditions. In our newer theory, we use this response function R of t of the form R of t equals mu times 1 minus e to the power of minus t over tau, where tau is the rise time or the relaxation time and mu is the mobility. And this particular form of the response function is actually naturally physically motivated by the response function of a particle in a viscous medium. And it turns out that this newer response function satisfies these two crucial positivity requirements and thus gives consistent results for all time t. This is to be contrasted with our earlier theoretical choice of the response function, where we chose the step function response function of the form R of t equals mu times theta of t minus tau. Now, from the sketch of the two response functions, you can see that one goes smoothly from, the newer one goes smoothly from 0 and climbs up to the value mu at times much larger than tau. Whereas in the step function situation, it goes abruptly to the constant value mu at t equal to tau and stays there. So at large times, both these response functions behave similarly. So the long time behavior for the diffusion does give the same expression in both cases. In both cases, we will get mean square displacement growing logarithmically with time. But when one goes to times close to tau, certain inconsistencies show up, which doesn't happen for the newer response function. In the step function situation, the earlier response function, there are inconsistencies which show up precisely because the earlier response function violates these crucial positivity requirements. I mean, the main reason why we used this simpler form was because of analytical tractability, and it gives reasonable results for large times. But there are these crucial positivity requirements which are violated at short times, which leads to inconsistencies, which I'll elaborate on further as we go along. So in particular, if for the earlier choice of the response function, the R of t equals mu times theta of t minus tau, we get this kind of an expression for the mean square displacement versus time, which gives perfectly consistent results for t much greater than tau. But for t close to tau, and for t less than tau, for very short times, we find that there is a clear inconsistency appearing. For instance, the left-hand side, which is the mean square displacement, is a manifestly positive quantity, whereas the right-hand side turns out to be negative as t tends to tau. So the deeper reason behind this is the fact that this step function response function violates these positivity requirements. So now let's go to the first positivity condition, the Weitman positivity. The two-point Weitman function, W of t, is given by this expression. X is the expectation value of x of t times x of 0. So it's essentially a correlation function. So Weitman positivity translates in the Fourier domain as W tilde of nu being positive. And the fluctuation dissipation theorem can be expressed in terms of the Fourier transform of the Weitman function in this form. W tilde of minus nu equals e to the power of 2 pi beta h bar nu times w tilde of nu. And it can be re-expressed in terms of a relation between the Weitman function and the response function in the Fourier domain in terms of this boxed equation. So w tilde of nu equals IH bar over 1 minus e to the power of 2 pi beta h bar nu times the Fourier transform of the response function. So you can see that the requirement of Weitman positivity, w tilde nu being positive, translates to the requirement of this, the Fourier transform of the response function times this factor being positive. Passivity. Passivity is essentially, as I mentioned earlier, is a statement of the second law of thermodynamics. And it says that the work done on the system, on a system in thermal equilibrium, is positive. So the work expressed as W bar, I've just written it to distinguish it from the Weitman function, is the time integral of the power, and which is in this particular case can be written as f of t times expectation value of the time derivative of the position. And the expectation value of the velocity in turn can be written in this form as a convolution of the velocity response function k of t and the perturbing force f of t. And where the velocity response function is related to the position response function r of t as k of t equals the time derivative of the position response function r of t. Now, plugging in this convolution expression of the expectation value of the velocity in the expression for the work, we, after some manipulation, just writing it in terms of Fourier transforms, we arrive at this equality that the work done equals 2 times 0 to infinity the integral over the frequency, real part of k tilde of nu times mod of f tilde of nu whole square, which for arbitrary force translates to the requirement that the real part of the Fourier transform of the velocity response function is positive. So the passivity requirement, this positivity requirement, which is the passivity, translates to the requirement that the real part of the Fourier transform of the velocity response function is positive. And we explicitly check that the new response function r of t, which is mu times 1 minus e to the power of minus t over tau, indeed satisfies these two positivity conditions, the Weitman positivity and passivity. In particular, if we consider this equation which we derived earlier, w tilde of nu, this connection between w tilde of nu and r tilde of nu. So given the expression for the response function in time, we can go to the Fourier domain and find out r tilde of nu and plug it to the right-hand side. And what we find is that Weitman positivity is indeed satisfied by this newer response function. Likewise, passivity can also be tested, and we find that if we start with the response function r of t and take the time derivative and find out the velocity response function in the time domain, and then take the Fourier transform of it and take the real part, we find that it's indeed positive. And thus we find that in our improved theory, the new response function indeed satisfies these two crucial positivity conditions. Although I have not gone over it, one can check that these two positivity conditions are indeed violated for the earlier response function R of t equals mu times theta of t minus tau. And if there's a breakdown of these positivity conditions for times shorter than tau. One can express the fluctuation dissipation theorem in terms of the Fourier transform of the velocity response function and the Fourier transform of the Weitmann function as follows. This is the relation. So real part of the Fourier transform of the velocity response function is related to the Fourier transform of the Weitmann function via this factor. One can sort of see how these steps would come about, because already we saw a connection between the Fourier transform of the Weitmann function and the Fourier transform of the position response function. And since the position response function and the velocity response function are related by a time derivative, which in the Fourier domain would involve a factor of mu, one can derive this connection. Now, this connection gives us something quite interesting. It tells us that if the real part of the Fourier transform of the velocity response function is positive, then that implies that the Fourier transform of the Weitmann function is positive, and vice versa. So we thus notice that Weitmann positivity implies passivity and vice versa. So that's quite interesting. The requirement of Weitmann positivity is quite general. It's just the requirement of the positivity of the Hilbert space inner product. Since it's the expectation value of x of t times x of 0, it's like taking the two kits, x of 0 and x of t, and sandwiching them and requiring that inner product to be positive. Whereas, in contrast, the requirement of passivity, on the other hand, reflects a very special property of systems in thermal equilibrium, that one cannot extract work from them by purely mechanical means. It is therefore noteworthy that we have here derived passivity simply from Weitmann positivity and the fluctuation dissipation theorem. This indicates that the fluctuation dissipation theorem manages to capture a surprisingly large part of the essence of thermal equilibrium. So here I'm displaying the results of our study. So with a newer response function, as I had mentioned earlier, that in contrast to the earlier one, which breaks down at times less than tau because of the breakdown of the positivity conditions, the newer response function is fully consistent for all values of time. Thus, we have a series of predictions over the entire range of time for the mean square displacements versus time. In particular, let's focus on the results for t much greater than tau. Just to recall, the times which appear in this problem, the various time scales are tau, which is the rise time or the relaxation time, and t, which is the observation time, and t thermal, which is the thermal time. So these three time scales come into play, and the interplay of them determine the various regimes. So for t much less than tau, we have these two interesting regimes. One is the quantum end, and the other one is the classical end. And remember that T thermal is proportional to beta. So clearly for beta tending to infinity, or T tending to, or the temperature tending to 0, we are in the quantum domain. And when the thermal time is very short, we are in the classical domain. And in the quantum domain, we get this mean square displacement growing logarithmically with time, this growth law. And in the classical domain, we, of course, recover the usual Einstein relation of the linear growth with time of the mean square displacement. Now, one detail to notice that the earlier step function response function gives this dashed curve as the prediction, whereas the newer one gives this solid curve as the prediction. So although in both cases we get a logarithmic growth of diffusion, there is a difference, quantitative difference between the two, which is characterized by this difference in the intercept. And in the quantum domain in particular, we have estimated a time temperature domain where this logarithmic quantum law of diffusion can be tested. And of course, the classical law is true at room temperatures. And one more interesting regime is there, which is again for T much greater than tau. But now the thermal time is in between these two times. So in this intermediate time temperature domain, we again get these two sets of predictions, one for the earlier response function and the another one for the newer response function. And as I had mentioned earlier, the dashed curve corresponds to an earlier prediction and the solid one for the newer one. But one very interesting feature of this intermediate time domain analytical prediction is that the mean square displacement has a piece which is like the classical growth law, which is basically a linear mean square displacement growing linearly with time. But in addition, there is a part which involves this logarithmic growth law. In particular, what you see here is it's a constant piece pertaining to the logarithmic law for T equals T thermal. So as if it's like a quantum remnant from a quantum era, in the following sense that in the quantum domain, the growth law is logarithmic, and in the classical domain, the growth law is linear with time. But even in the intermediate time temperature domain, as if apart from the classical piece, there is a remnant of the quantum era indicated by this logarithm of T thermal over 2 tau. And here also we have a time temperature domain, which we can estimate for to be tested in the laboratory, in the cold atom laboratory. Apart from these time domains, the new response function has opened up another time window, which is T much less than tau, which was inaccessible in the case of the earlier response function, because in the earlier case, there was an inconsistency showing up in this time domain because of the breakdown of the positivity conditions. So that's also very nice that we have two sets of predictions in the time, in the observation time much less than tau domain. One for T thermal being very large, which is the equivalent to saying that it's in the extreme quantum domain, and also in the intermediate time temperature domain. So these also can be tested. So more recently, we have actually gone back to a microscopic model. This work was done with Abhijit Das, Abhishek Dhar, Ayan Satra, and Urvashi Satpathy, and it's published in Physical Review E last year. So this model is basically a system environment model where we have a particle, it's a harmonic oscillator, coupled to a chain of harmonic oscillators, which is a bath. And this is called the Rubin model. And here the Hamiltonian consists of a system part, a bath part, and a system bath coupling part. So I'm just schematically giving just stating what was done in the work. So we arrive at the effective quantum Langevin equation for the particle by integrating out the bath degrees of freedom. And this is the form of the quantum Langevin equation. Notice the appearance of the dissipative kernel gamma of t, which is connected to the noise kernel eta of t via the fluctuation dissipation relation. And what we do here is we study the one-dimensional harmonic chain model, the Rubin model, bath model, and its continuum limits, the Trude and the ohmic models. So this particular harmonic chain model in the continuum limit gives rise to these two interesting known models, Trude and ohmic. And for all these three bath models, we find that in the zero temperature quantum domain, the mean square displacement grows logarithmically with time. And this confirms our earlier claim based on the fluctuation dissipation theorem that the logarithmic law of diffusion is model independent. At finite temperatures, there is a crossover from the logarithmic law to the linear law of growth of the mean square displacement at a crossover time given by the thermal time. And another motivation behind our studying this particular microscopic model was to compute the response function and thus finding an underlying justification for the choice of the response function, which is a key input to our analysis based on the fluctuation dissipation theorem. And we indeed recovered the response function of the form R of t equals mu times 1 minus e to the power of minus t over tau, which was used as in our newer improved theory. We indeed recovered that in the continuum limit. More recently, we did a theory experiment collaborative work with a group of experimenters, Shubhajit Bhar, Maheshwar Shah, Saptarishi Chaudhuri and Samyukta Rai. And Urvashi Satpathy, Raphael Sorkin, and I were the theorists in the collaboration. And it's available on the archive. And so our final goal is to be able to measure and analyze the mean square displacement as a function of time in the quantum domain. But as a prelude to that, we thought that it would be a good idea to just measure the response function and analyze that. And that was quite an interesting thing to do. So the experiment consisted of considering a cold atomic cloud of rubidium trapped in a magneto-optic trap and embedded in a 3D optical molasses. So the magneto-optic trap provided a spring-like force and the optical molasses provided a viscous force. So the resulting response function in this particular case was has this oscillatory component, and it's like a damped oscillatory function. And we analyzed it via a quantum Langevin equation where we incorporated a spring force to account for the magneto-optic trap and a viscous force to account for the 3D optical molasses. And this is the red curve is our theoretical prediction, and these are the experimental points. So one can view the response function that we have used in our fluctuation dissipation theorem based theory as the limit of these kind of response functions in a situation where the magneto-optic trap spring force tends to 0 and we are in the overdamped limit. And then there we expect to get that functional form that we have used in our model, in our theoretical analysis based on the fluctuation dissipation theorem. So just to conclude, we use the fluctuation dissipation theorem as a starting point for analyzing the growth of the mean square displacement with time. The only input is the position response function R of t. The logarithmic quantum diffusion behavior is robust. That is, it's same for both R of t, the one that we had used earlier, which was the cruder response function, mu times theta of t minus tau, and the newer improved one, which is mu times 1 minus e to the power minus t over tau. The new response function, R of t equals mu times 1 minus e to the power minus t over tau, satisfies the positivity requirements, Weitman positivity and passivity, that are crucial for a physically viable response function. The new R of t enables us to probe the t much less than tau regime, which was inaccessible in the case of the cruder theta function response function. We have a recent theory experiment collaborative paper where we have presented an analysis and measurement of the response function R of t using cold atoms. And in future, we intend to probe and analyze the very low temperature deep quantum regime and test the logarithmic law of diffusion. So thank you. I just want to show the relevant papers, which I have already mentioned. Brownian motion at absolute zero, which was published in 1992. Raphael Sorkin and I have done the work. Physical Review B it was published in. Then more recently, we had done a work which was published in JSTAT in 2017. Work done with Urvashi Satpathy and Raphael Sorkin, a quantum diffusion law. And subsequently, we did this work, quantum Brownian motion, Drude and ohmic baths as continuum limits of the Rubin model. This work done with Abhijit Das, Abhishek Dhar, Ayan Shatra, and Urvashi Satpathy, published in Physical Review E last year. And most recently, we have done this theory experiment collaborative work, which is available on the archive. Thanks for your attention.
Very nice. Thank you so much. We can unmute ourselves and ask questions. The floor is open.
Yes, Surajit, I have a question.
Yeah, Gamana, go ahead.
So am I right to assume that you had these results for the positivity because RT was smooth at zero?
This you mean the fact that R of you're saying that in the earlier case there was an abrupt rise.
There was a discontinuity, right?
Here you are smoothing it over.
At least it's continuous.
Yeah. It's continuous.
Yeah.
And
is that the reason for the positive?
I'm not 100% sure that any continuous function like that, a continuous function with which goes over to t equal to for t much greater than tau goes over to a constant would necessarily give satisfy this condition, because if you look, I'm not 100% sure about that, because I in this case I can see explicitly that you start with the
right, okay, yeah,
and then you work out and you see that it's indeed true. But a priori, I'm not completely sure whether you can take any arbitrary continuous function like that and see that it satisfies these positivity requirements.
I see.
But one can try out other functions and see how it works.
So the one thing I would have thought was, see, even this function is, even though it's continuous, it's not differentiable. So if you put it differentiability as well, for example, to a Hill function, then will it would the properties be different?
Let's see. I'll just go back to this function. The
Yeah.
function looks like this, which is like this.
Right. So it's not differentiable at 0.
At time t equal to 0.
Well, because the left side is 0, right? The derivative is 0 on the left side. I don't know if I'm just thinking aloud if these things are important.
No. Why is this? So like when you take the time derivative of this, that's what is the velocity response function,
Right. Yes.
And if you take the time derivative of this, why would you say that it's
Well, it has a slope on the positive side, but it's 0 on the negative. The slope is 0 on the negative side.
Okay, you're saying that because of the presence of the theta function,
Right.
that's the reason why you're saying that. Yeah, I understand.
Yeah.
So the derivative of the theta function will give you a delta function.
Right. That's right. Yes.
Mm-hmm.
So I was just wondering if that how important the smoothness was. So if that was the reason you got.
Yeah, that's an interesting question. I haven't really thought about it that much. That how general, I mean, what are the what are the conditions needed for the response function to satisfy so that the positivity is guaranteed? Like,
right, that's right.
Yeah.
Thank you very much.
Thanks. Thanks for your question.
Further questions? So I had similar questions also. One question I had is, instead of taking an exponential function, which clearly is tied to a time scale, what if you have a scale-free system in terms of relaxation? There are many examples where you actually get algebraic relaxation behavior. So if the response function has algebraic property as opposed to something with a scale, one should be able to still recover logarithmic laws. It would seem like a more general behavior may be tolerable.
Actually, yeah, I'll tell you one thing. If you look at the choice of the response function here, R of t, this particular thing that we have chosen, this is very much physically motivated by the choice of by the response of a particle in a viscous medium. So that looks like the most physically compelling reason for the choice of the response function. One could, in principle, think of any other response functions. Of course, it has to be consistent with those positivity requirements, because the passivity, for example, if passivity is not satisfied, that would be equivalent to saying that second law is violated. And likewise, this Whiteman positivity also has to be satisfied. And of course, I mean, your question is sort of related to the fact that even if we forget about the quantum domain, say, for example, classically also, in the classical domain, you do have Levy flights and other kinds of diffusion processes, right? So in principle, you can think of things of that kind. But here we are restricting our inquiry to the following thing, that what is the quantum domain counterpart of Einstein's law of diffusion?
Yeah, so it's more Brownian regime.
Yeah, it's the Brownian regime. Right.
Yeah, so, okay. I think the other thing was that whether the logarithmic law sheds any insights into stuff like quantum turbulence. Because the quantum nature seems to play a substantive role.
Right.
And so in quantum fluids, especially in noisy circumstances in quantum fluids, it would seem that a behavior like this may be of interest from that side. Actually, Christina also left a very interesting question.
Oh, okay.
And
I don't know till what
I'll read it out.
Christina was there.
Yeah, Christina left about 20 minutes ago.
Oh, okay.
She said, as I mentioned, unfortunately, I have to leave early, but very interesting work. Can it be generalized to a quantum active particle? In this case, you do not have fluctuation dissipation theorem, though.
That's a very interesting, interesting question. Yeah, one thing is that this whole work, this work that we have done is completely based on the fluctuation dissipation theorem. So now the question is, if you give it up, what happens? But on the other hand, one can still ask what would happen to an active particle which is driven by 0 point fluctuations rather than thermal fluctuations. That's an interesting question, certainly.
Any other questions? If not, we'll thank Supurna for
I have a question.
Yeah, go ahead, Shapin.
Yeah, thank you. It's very nice talk.
Thank you.
Yeah, I'm not very familiar with the no temperature and the quantum system for the diffusion behavior, but I'm working with the granular materials. So it's a thermal system. People believe that it's a kind of very low temperature. I mean,
yeah,
it's so low temperature.
Like, for example, you can think of a vibrated granular system.
Yeah, completely. So when you show your heat pass model for the Rubin model, I just learned from you, it's a kind of the coupling of the vibration. I mean, of your Brownian particles with the heat pass. So I'm wondering how this model, I mean, this specific slowdown, I mean, it's a logarithmic diffusion behavior matter in the granular system, of course, under the external vibration, because sometimes people said, okay, this kind of external vibration could be modeled as a kind of a temperature. It's not very easy, but you give me, when you look at your Rubin heat pass model, it looks like, I mean, it could be related, it seems to me very easily to the external vibration. It's not very easy because the external vibration could be coherent or random. It's another story. But we do observe in the experiments when you vibrate your granular system, not only you may have a coherent motion, but you can also induce the kind of a non-affine, I mean, the random motion of the particles. Yeah, I don't know if I'm clear. So I want to say, what is the possible link we can generalize your model to the granular system?
Yeah, I think the in the context of driven granular system, the issue of how to define a temperature itself is a sort of a disputed idea. I mean, various people define it in various different ways, right?
Yes.
Yeah, and I don't know the issue of fluctuation dissipation theorem, to what extent it has been sort of probed in the context of granular system. I think they see violation? I think they do see violations in certain cases.
Yeah, but in some cases, I think there's some publication. Suraj probably knows that the people from the simulation and also from the experiments, there's a group in the Switzerland, Dana, I don't know if they do some experiments about 20 years ago, published in Nature, just to say, well, the external vibration produce a kind of random motion, and they utilize a kind of a torsional oscillator probe.
Actually, now that you mention it, I think I remember seeing this paper, and they are actually establishing the fluctuation dissipation relation.
Yeah.
Isn't it? Yeah. In that case, they see that it is actually indeed valid. Indeed. Yeah. That's correct. So one could think of perhaps applying it there in situations where the fluctuation dissipation theorem is actually satisfied, even in the granular context.
One thought about Xiaoping's point may be that this is really like a cold viscous medium, because the thermal motion is so short range, right? And it's so localized. So it's like a viscous medium, but it's also very cold because the thermal part of it is quite weak.
Yeah.
Quickly goes away. Yeah, that's a very interesting problem. I mean, this is a fascinating range of issues that we are discussing. Yeah, I also remembered this paper, but I haven't seen too much work on the fluctuation dissipation.
Yeah,
No,
actually, I after he mentioned, I suddenly it came back to me that I had seen this paper. In fact, because we ourselves in our institute, we have a small lab which we call the theorist lab. So only theorists go there, and we were doing some experiments on vibrated granular matter. So we were doing this. We took some mustard seeds and put it on a plate, and with a speaker underneath, very rudimentary form of experiments. So I remember at that time we were thinking about these issues, and this paper caught our attention. The fluctuation. Yeah.
yeah.
This is the paper by Diana, is it?
I think so.
Dana, yeah, I don't.
Giancarlo Diana?
Yeah, it's from the EPFR, EPFR of
in
Switzerland. Yeah,
I had invited him in my 2020 MRS meeting.
Yeah, probably. You're completely right.
You
yeah,
come
it
there,
comes back at the very beginning. But here, what I'm very excited by this model, we just on the screen, because I did not realize that the temperature for the, I mean, even in the thermodynamics system could be modelized with the harmonic oscillators in that way. So it gives us from a macroscopic system like brand medium, it's just kind of external vibration. So it it really
that's an
fascinating.
Interesting direction to explore. That's true.
Yeah.
And Xiaoping does some amazing experiments in his lab in Paris. So he probably can do some.
For the vibration, it's really sound propagating, just like Suraji, we know each other on such a topic. So thank you very much. It really is very nice. So we hope talk later.
Yeah, you guys should correspond about this. Okay.
Sure.
Any further questions? If not, then we will.
I have a question, sorry.
Yeah, go ahead.
So maybe I have a question in another perspective, but related to the previous question is for the classical point of view, this kind of classical correlation, we use Langevin equation.
Yeah.
So I want to ask you if you think in the possibility to have a Langevin equation that we obtain logarithmic correlation. So have you thinking what kind of noise we have in order to obtain this kind of correlations?
So what happens is that, in fact, if you look at this paper, this paper that we have written, Physical Review 2020, that paper. So there, in fact, we have derived a quantum Langevin equation. It's the quantum version of the Langevin equation, where we have investigated this mean square displacement growth, and we get this logarithmic law of diffusion from there, from a quantum Langevin equation. And the important point, in fact, the one that I wanted to draw attention to. So if you look at, in fact, here in this slide itself, you see the fluctuation dissipation relation, which connects the noise correlation with the dissipative kernel, gamma of omega. And what happens is in the quantum domain, this function that this is like the Bose function, which comes into play, e to the power of beta h bar omega minus 1 to the power of minus 1. This, because of this non-trivial function, what happens is that if you go to the time domain, it makes it even clearer that the noise correlation is non-Markovian in the quantum domain. It is not delta correlated, but it has non-trivial temporal correlations. And that is, in fact, the crucial reason why one gets a logarithmic law of diffusion. So what happens is in the high temperature classical limit, this noise correlation becomes trivial. It becomes a delta correlation, and you end up with a linear growth. So that's the,
That's
you are
not-
absolutely right about the fact that the quantum Langevin equation leads to has this non-trivial noise correlation, which indeed gives us that logarithmic law of diffusion.
Yeah.
Okay, perfect. I will read carefully. Thanks a lot.
Yeah, this is very interesting. I suspect that it's more general than exponential that probably would give this logarithmic behavior, but that's just a guess.
Mhm.
So,
I agree.
any other questions? All right. In that case, let's thank Supurna again. You can unmute yourself and make a lot of noise.
Thanks.
This is very
Thank
nice.
you.
Sorry about
Thanks
all
for your
the
attention and-
extra
and,
hoopla.
questions. Yeah, that is another. I mean, I remember last time when during Chandan Das Gupta's talk, this
Yeah.
happened. After that, I thought you had put some
I
extra
did.
restrictions
I
or
did.
something.
I did. Actually, what happened was that sometimes what happens is somebody would not send me an intimation and would still come in. So there's always an iota of guesswork involved in one or two people who would knock at the door. So I must have slipped somewhere because I was introducing you and also letting people in. So yeah, so after that, this is the next time it happened. So I must have slipped.
Yeah.
One of the,
Because
because
there's a big gap actually now. I mean, between
one of the things that happens is that, and this is very unfortunate, but there is little privacy in Zoom because many of the servers are through mainland China. So there has been a study from University of Toronto recently in which they have recorded a complete cabinet meeting of Boris Johnson.
Oh,
Right. So that was just one of the few shocking things that happens. So in spite of all the claims, there is a severe lack of privacy in Zoom that can happen. And so I only admit people who I know for that reason.
that's the safer thing.
That's the safest thing to do. And I say that's what in the email. But today I must have slipped because I have a few newer students and I must have
So
confused a name.
Yeah, that's right. It's hard to keep track of the names of all the students.
Yeah, I'm pretty sure that's what happened. You only need one slip, by the way.
Yeah. That would be enough. Yeah.
Yeah, one slip is enough.
Right.
So I must have, because I often would not let somebody in and then I would get an email, you didn't let me in. But today I slipped with somebody and I think I know who it is. Yeah, because this person tried again.
Oh, okay.
Yeah.
So it's a known person, basically.
At least the name was known the second time around. The first time the name looked familiar because there are some newer students and I think this person was a student. That's what I thought, but I think that was partly or could have been part of the problem. Anyway, we prevented that at the second time.
Yeah, all is well that ends well.
All is well. Yes. Thank you, Supurna, for a beautiful talk, and we'll be in touch.
Thanks for your attention, and
Bye-bye.
thanks for all the questions.
Have a great weekend.
Bye.
Bye-bye.
Bye-bye.
Bye-bye.